regarding exercise 1C, question 7, 9, 11, 13, would have. Question, exercise 2A, question 10. Don't have also. What question? 10? Question 10. Okay, let's look at exercise 2A, question 10 then. What is the issue that you face? Which part or which section of the question? Is it about listing the sample space? The listing part. But part I, 2 and 3 you can do? Okay. Now let's run through. Alright, let's see exercise 2A. Question 10. Okay, in question 10, right, it says that the 3 daughters-in-law of Mrs. Chan are happily waiting the arrival of their bundles of joy within the year. Okay, how cheesy. This is the sample space of the sexes of the 3 babies, given that the babies are equally likely to be a boy or a girl. Okay, so we let B to represent a boy. Okay, and G to represent a girl. Right? And also S, okay, to represent the sample space. So, our sample space, okay, we'll look at the different combinations of grandchildren that this Mrs. Chan could have. Alright, so since there are 3 daughters-in-law, okay, so it can be all boys. Right? It can also be maybe boy, girl, boy. Okay, meaning to say the first daughter-in-law gets a boy, second one is a girl, third one is a boy. Okay, we can also have first one to be a boy, second one to be a boy, third one to be a girl. Then we can also have girl, boy, 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 girl, 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 boy, girl, 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 boy, and all those. Okay. Then in part I, to find the probability of having 3 grandsons. Okay, because there is a total of 8 different possibilities here, but to have 3 grandsons is only 1 out of 8. So therefore answer 1 out of 8. Then to have 2 grandsons and 1 granddaughter, that would be this, and this one. Okay, so that is 3 out of 8. And the last one, to have 1 grandson and 2 granddaughters. So 1 grandson will be here, this 3, and having 2 granddaughters will be this 3 here. So it is also 3 over 8. Okay, clarified? Any other questions? Otherwise, you may submit your homework to the front. executed. 23. Any absentee? Yeah, count already. Okay, then please count. 1, 2, 3, 4, 5, 6, 7, 8, huh? Oh, okay. You want to update here?
The Dylan is always in the class.
In your heart, is it?
Oh.
What happened to him again? Huh? Trapped in Joseph's heart.
No.
Okay, let's move on. Alright, so the last lesson I've introduced to you possibility diagrams. Okay, did you all manage to do the practice now for question 2? If you all do? Never do? Okay, never do, I also don't want to go through already. Yeah, because it's standard lah. How many of you never do question 2? Practice now for question 2. Because it's the same set. I think when it comes to possibility diagrams, you all are more or less there. Okay, so I just want to go directly into 3 diagrams instead. This is 2.2. Okay, we'll focus on 3 diagrams, although it's still under chapter 2.2. Alright, why is it that we need to learn 3 diagrams when we already know possibility diagrams? The reason is because there is a limitation when it comes to possibility diagrams. The limitation for possibility diagram is that we can only have 2 possibility diagram. Okay, we can only have 2 different outcomes. 2 components. Okay, we can only have 2 components, 1 on each axis. What if I have 3 components? Let's say if I am going to roll a die. Okay, roll a die, I want to roll it 3 times. Okay, and each time in roll, I want to record down what is the number. Then if it comes to that, I'm not able to use a possibility diagram anymore. Because possibility diagram can only allow me to have up to 2 times of rolling the die. Right? So that's why we need to have the 3 diagram which will allow for that. Okay, so let us maybe consider flipping the coin. Okay, so let's start with something simple first. Flipping a fair coin. Okay, 3 fair coins. So since we have 3 coins, we are looking at first coin, second coin, and third coin. Okay, you need to give yourself sufficient space first, so don't need to write this yet. Okay, so when it comes to flipping a coin, it's either getting a head or a tail. So in the first coin, we will have head or tail. So H to represent head and then T to represent tail. Because these are the only 2 possible outcomes for first coin. Right? Then I want to follow through. I flipped the first coin already. I want to flip the second coin. So I leave the first coin untouched. Let's say the first coin is H. Then when it comes to the second coin, I can also either be getting head or tail. If my first coin is tail, my second coin can also either be head or tail. Okay? Then when it comes to my third coin, let's say first and second are both heads already. My third coin I can have head or tail. Head or tail. Head or tail. Sorry, running out of space. Let me adjust this a bit. Okay, so after the second coin, we branch out again, alright, considering the head or tail. Okay, so this is the reason why, based on the look of it, we call it a tree diagram. Okay, because of the whole branching out effect. When it comes to drawing your tree diagram, please ensure that you have sufficient space. Okay, leave enough space, locate somewhere the center, and then you start drawing, expanding. Okay, I don't want a tree diagram that ends up, okay, maybe you squeeze it over to one side, that it is slanted, and then you end up writing smaller and smaller. Okay, of course I have the free reign of the whiteboard, so it is okay. But when it comes to your work, please draw it neatly. Use a ruler to draw the lines. Okay, you need to have the lines, and then after ensure there's sufficient space. Okay. Then also in a tree diagram, you should label, right, what is the component per column. First coin, second coin, third coin, depending on the situation of the question. Okay. So I'll use this diagram, okay, to illustrate on how do we determine the probability, right, of getting 2 heads, 1 tail, as well as at least 1 tail. Okay, so having the a tree diagram itself allows me to see the overall picture. Okay, I can see the exact outcome per coin. Okay, so at the end of the day, okay, when it comes to probability, what is the sample space like? Okay, it allows me to see that the first possibility is to have 3 heads, that means 3 heads. Okay, another possibility is maybe 2 heads and 1 tail. So you can follow along the branches. Then we can also have 1 head, 1 tail, then the second head over here. Then after that, we can also have HTT, THH, THT, TTH, and TTT. Okay, so there is a total of 8 possibilities, alright, 8 different possible outcomes. Alright, so we can count right at the end what are the different outcomes that are possible. Any questions so far? Okay, so if let's say I want to see the probability of getting 2 heads and 1 tail, right? How do we determine it? We want 2 heads. So it can be the first one and the second one to be a head. And then after that we get a tail. So this fulfills the criteria, the event that we're looking at. There is another possibility, which is to have head first, then tail, then head, which is also 2 heads and 1 tail. So this is another possibility that fulfills that event. Okay? We can also have, let's say, 1 tail, then head and head again, right? And we could also have, do we have another one? Don't have. Okay? So we see that there are 3 different possibilities that actually satisfy this event. So answer will be 3 over 8, because total there are 8 different combinations that we can arrive at. Right? Then what about getting at least 1 tail? At least 1 tail means that you need to have 1 tail in that combination, 2 tails in that combination, otherwise 3 tails in the combination. Okay? So you can go about counting it. Having 1 tail will be having this one here. 1 tail can also be this one. The other combination, HTT, also fulfills that, so we can also have this. Then for all, okay, that starts with this tail here first, okay, surely it will fulfill the criteria, right? Because you have tail, head, head, tail, head, tail, at least 1 tail, right? Okay, so all of this here. And we see that there are 7 of them over here. So by counting the different cases that we can have, we get 7 over 8. Okay? An alternative way of saying this question and understanding it is that having at least 1 tail, the opposite case will be probability of having no tail. Okay? And having no tail is the same as saying all H. So I could see 1 minus the probability of no tail, or 1 minus the probability of all H. And the probability of getting all H is 1 out of 8, which also leaves us with 7 over 8. Understand what I'm saying? Okay. Next, look at practice down 5, question 1. We are referring to this dart player, who's Michael. Okay, there is an equal probability that he will hit or miss the bullseye, and he attempts it in 3 throws. We want to draw a tree diagram, okay, to help us to find the probabilities for these 2 events here. Okay, since you're looking at 3 throws, so we will have 3 columns. Okay. Starting with either hit or miss. So you can let H be representing hitting, or M to be missing. Okay, so this is the first attempt. Usually I suggest at the start, right, to draw it wider, right? The angle of the branches itself be wider, so that you can branch out. Then we have to look at the second throw. And finally, the third throw. Okay, so what is the probability that Michael will actually miss the bullseye once? What do you think the probability will be, Joseph? What's the probability going to be like for Michael to miss the bullseye once? Three over 8. How do you get 3 over 8? Can you tell me which one fulfills that criteria? 1, 2, 3, 4, all the way to 8. Number 2? Okay, and then 3? 5, 2, 3, 4, 5. Okay, so we see that along this branch, hit, hit, and miss, that is missing it once. Then we have hit, miss, hit, missing once also. And then we have miss, hit, hit, alright, which is also missing once. Right, so we see that there are 3 that actually fulfills the event out of a total of 8. Okay? Then what's the probability of hitting bullseye at least once? Okay, Jin-Yang, can you tell me what will your answer be? 7 over 8. Can you tell me how do you get 7 over 8? Do you count? Or okay, so we have the all miss over here, right? That doesn't fulfill the criteria. Otherwise, everything else hits at least once. So therefore, answer is 7 over 8 for part 2. Okay. Now, let's look at question 2. Okay, in your textbook itself, there is an incomplete tree diagram. So there are times where in the exam even, they also give you an incomplete tree diagram and expect you to complete it. Okay, so they have given you box A, whereby there are 1, 2, 3 and 4 on the pieces of paper found in box A. And then in box B, they actually have it incomplete, where they gave you only 1 and 2. Okay, so to complete it, we will continue the same pattern. Since box B can only have 2 numbers, so we have 1, 2, 1, 2, and 1, 2. Okay, what would the probability be to get at least one octave if this is the tree diagram? What would the probability be? Li Hui, what do you think? Probability of at least one octave. Five over 8. How do you get 5 over 8? Which one did you choose? If it's 1, 2, 3, 4, 5, 6, 7, 8. 1? Sorry? 2, okay. 3, 5, 7, okay. So this will be what you choose. By the way, you don't need to actually put a tick one up, alright? It is not really a working. Okay, you can just count and then write down your probability. Okay, in part 2, we want to find the probability that the sum of 2 numbers is 3. So one thing that is okay, of your tree diagram is that there is no way for us to determine the sum and product, like how we have a possibility diagram for sum and product. Okay, and in fact, in this case, right, even if you want to do a possibility diagram, it is possible. Okay, because there are only 2 components. Alright, just that in this particular question, they gave you a tree diagram and wanted you to complete it already. Right, so you do find subsequently that having a tree diagram is more useful as compared to a possibility diagram. But of course, look up at what the question was. So since we are looking at the sum, what we will usually do is to create one column that describes the sum. Okay, so you just quickly add up the numbers. So 2, 3, 3, 4, 4, 5, 5, 6. Okay, add up the numbers along that branch itself that will result in that sum. Okay, so what would the probability be where the sum of the 2 numbers is 3? The answer, Noi? 1/4. How do you get 1/4? Okay, so second and the third one, the sum is 3, so that is 2 out of 8. So simplify your answer 1/4. It is very common that when it comes to probability, people tend to forget to simplify. So remember to simplify your answers. Alright? I'd like you to do the same, okay, for part 3 and part 4. Determine the product Okay, and determine the probability. Okay, so in part 2, part 3. Finish it with. Yes, Session. Yes. Give you a minute. Okay, so what's the probability for part 3, Kelly? Sorry? Half. Okay, so let's see, what's the answer? Okay, so we want the product of two numbers is at least 4, so your product should be 1, 2, 2, 4, 3, 6, 4, 8. Okay, so if you were to look at that, you should get 4 over 8. Which is equals to half. And then part 4, what will your answer be, Carissa? 1 over 8. Okay, so the only one is this one here, where sum and product are equal. Okay, so with that, we have some idea about tree diagrams. So homework for exercise 2A. Okay. We have already done 1 for question 10. So let me write in basic order. Question 7, 11, 12, 13. Okay, I'll let it be due on Friday. Right? So tomorrow, if you have finished the homework, the worksheet earlier, you can just work on that. Okay, so don't need to waste the time at home. Right? Let's look at the time by lesson N40, right? Let's look at 2.3. We delve deeper into our tree diagram. Write down the meaning of mutually exclusive on the whiteboard first. So you may like to copy it down. Okay, just 30 seconds, copy. Okay, so let me just explain about mutually exclusive and also non-mutually exclusive events. Right? These are words and terms that we often see when it comes to probability. Okay, so let's have just an example. Okay, if I have 8 cards in the box, right? So they are numbered 1, 2, 3, 4, 5, 6, 7, 8. Okay, so if I were to let A to be the event of drawing of prime number, and let B be the event of drawing a multiple of 4, and in C, drawing an odd number. Okay, so these are events, drawing as if you're taking a card out of this set of numbers here. Okay, if we look at the cards that are found in the event A itself. So let me just write it in a set. Okay, can you tell me what are the prime numbers that are satisfying the event A? Kajia, what do you think? 2, 3, 5, 7. That's all, right? Okay, so 1 is not a prime number. What about B, drawing a multiple of 4? Bervin? 4 and 8. And for the event C, drawing an odd number, that will be our 1, 3, 5, and 7. Right? Okay. So when we say that they are mutually exclusive, okay, it means that they cannot occur at the same time. So looking at the elements found in these events, right? Okay, which two sets are mutually exclusive? Meaning to say that they cannot occur at the same time. So by right, they should not share anything in common. What would it be? A and B, and B and C. So we see that between A and B, there's nothing in common. Okay, B and C, there's also nothing in common. So we say that A and B are mutually exclusive events. B and C are also mutually exclusive events. Okay? Then for non-mutually exclusive, it means that there is an overlap. Okay, and what would those two events be? Axel, what do you think? A and C. Okay, so we see that A and C, there is an overlap of 5 and 7. Anything else? No, right? Okay, so A and C are what we call non-mutually exclusive events. Okay, sorry. Thank you. Okay, so what do we understand about mutually exclusive and non-mutually exclusive events is if you would look closer at the probability itself. Okay, so let's look at the probability of A happening. So there are 4 outcomes, okay, that are favorable as compared to 8 possible outcomes in total. So the probability of having A is actually 4 out of 8. The probability of B will be 2 out of 8, and the probability of C itself, okay, would actually be 4 out of 8. Right? I'm just leaving it in this manner. I'm not simplifying it. Okay? Because I want to use it further. Right? So if you want to see for mutually exclusive event, okay, mutually exclusive events would be, for example, if I want to choose probability of A or B. Okay, so if I want to find, let's say if I ask a question, okay, that I want to find the probability of getting A or B, in words, it will mean that I want to get a prime number or a multiple of 4. If we solely look at this, ignoring about the others first, getting a prime number, 4 of them are prime numbers. Getting a multiple of 4, 2 of them are. So there are 6 of them that actually satisfy the event of prime number or multiple of 4. Okay, so 6 out of total of 8, we will see that the probability is 6 over 8. Agree? Okay, so 6 over 8, if we try to draw a pattern to the probabilities that we get over here, okay, we notice that probability of A is 4 over 8, probability of B is 2 over 8. So coincidentally, 4 over 8 plus 2 over 8 is actually equals to 6 over 8. Okay, so okay, so we observe this. Now what if I chose to compare between B and C? So the probability of B or probability of C. Okay, so meaning to say probability of getting a multiple of 4 or odd number. Okay, so looking at this statement itself, multiple of 4 there are 2 of them, odd number there are 4 of them. So we would have seen that total is 6, so 6 over 8. And coincidentally, the probability of B plus the probability of C is our 2 over 8 plus 4 over 8, which is 6 over 8. Okay? So let me draw a line here. So these two are actually mutually exclusive events. What if it is non-mutually exclusive? Okay? So we identified that A and C are actually non-mutually exclusive events. So if I were to look at the probability of A or C, meaning to say probability of having a prime number or an odd number, okay, our probability will be prime numbers, we have 4 of them, odd numbers, we have actually 4 of them here, but there is an overlap of 5 and 7. So technically, if we were to count directly from here, we will identify that there are 6, okay, which is 6 over 8 as the answer for the probability of prime number or odd number. Do we agree? Okay, because prime number, we have our 2, 3, 5, 7. If we want odd number also, we need to count in our 1. Oh, sorry, there's 5. My bad. Okay, so there's a total of 5. Okay, but if I were to consider probability of A plus probability of C, probability of A is 4 over 8. C is 4 over 8. It gives us 1 whole. Okay, so what am I trying to draw in conclusion over here is that if we are looking at mutually exclusive events, we can actually add the probabilities up. Okay, if they are non-mutually exclusive events, like A and C, okay, we cannot add the probabilities up. Right? And that is actually our addition law of probability. Okay? So usually in the exam, okay, if you see the word or, you may want to link it to the idea of plus. But you must always do a check. Okay? That having the word or doesn't always link to a plus. Because if it is a non-mutually exclusive event, then it will not add up together because these two are not equal. So you need to ensure that it is a mutually exclusive event first. Okay? Then you can do the addition. Alright? The reason why I need to talk about this addition because later on when you do tree diagrams, we will be exploring more about that. And usually we are looking at mutually exclusive events rather than non-mutually exclusive. Okay? Got the idea? Alright? So an example of mutually exclusive event, okay, would be if, okay, Bismarck is teaching in maths class and Joseph is sleeping. Are they mutually exclusive events or not? Mutually exclusive or not mutually exclusive? Not mutually exclusive. Okay, so not mutually means that they can occur at the same time. You mean can occur at the same time, by right? Are we supposed to be a mutually or non-mutually exclusive event? Mutually, so by right, I come in here, you shouldn't be sleeping. Okay, so you can keep that in mind. Alright, let's look at some examples. Okay, let's look at practice now 6. Okay, so we are looking at practice now 6 where we have 52 playing cards. Okay, so your usual deck of cards. Okay, you should be familiar with the deck of cards, right? For math purposes, not for other purposes. Okay, so we want to find in part I the probability of getting a picture card or ace. Right? For things like this, okay, it is familiar to us, so we can just do our usual counting. Okay, but we also recognize that drawing a picture card is a mutually exclusive event from drawing an ace. Because you cannot have an ace that is also a picture card. Right? So that's why in part I, okay, we can see that it is as good as thinking of probability of picture card plus probability of getting an ace. And how many picture cards are there? What is considered a picture card? King, Queen and Jack, right? Okay, in 52 playing cards, we do not count the Joker card. Usually we don't count in the Joker. Okay, 52 cards will be your number 1 to 10. 1 meaning your ace. Okay, ace to 10, your King, Queen, Jack. Okay, you all know your cards, right? Okay, so picture card will be your King, Queen and Jack. And since there are 4 different types, so therefore 3 times 4, that will be 12 out of 52. Then for the probability of ace, how many ace are there in total? 4, right? So 4 all over 52. And that would give us 4 over 13 as our final answer. I'd like you to very quickly do part 2, 3 and 4 to determine the probabilities. Everybody done? So what would the answer be part 2B? What is the probability for a's or number divisible by 3? Nicole, what do you get? 4 out of 13. Okay. So a's we have 4 of it. Plus number of divisible by 3, we actually have 12 of it. We will get 4 over 13. Divisible by 3 will be 3, 6, 9. Okay, and there are 4 different sets, so for 12 cards. What about part 3? What is the probability of getting a king or a queen, Bernice? 2 over 13, so there are 4 kings and 4 queens. So we get 2 over 13. Okay. Now what about part 4? Probability of neither jack nor queen. Oh, sorry, jack nor ace. What would that be? Jin Yang? How do you get 11 over 13? 1 minus 4 over 13. 4 over 52. Okay, so Jin Yang said 1 minus 4 over 52. Okay, the reason is because, sorry, let me just write it lower. 1 minus 4 over 52. Okay, when we talk about neither jack nor ace, right, it is actually as good as saying 1 minus the probability of getting a jack or ace. So we can think of the counter, okay, the opposite of it, right? So 1 minus getting a jack or ace, since there will be, okay, sure 4 over 52. 4 is the number of ace, right? So 1 minus 4 over 52 gives you 11 over 13. Oh, then minus again another 4 over 52. Okay? So there are 4 jacks and then 4 ace. So we can add them up to get this probability. 1 minus that, we get 11 over 13 as our final answer. Okay? Alright, so with this, I'll just end here today. Okay? Then on Friday, we will continue. And then we will also look at independent events and your multiplication law. Okay, thank you, class.